Alrighty, hopefully you had a chance to really try to prove this sequence here for deadlock freedom. I think definitely one challenge is to really identify, since now we got two sets of example rules, we got about 16 or so inference rules for you to really choose from. Definitely, eventually we'll get to even larger and larger set of inference rule for you to consider. And definitely one major challenge would be to find out those that are actually relevant to really discharge the sequence, or at least to do some transformation as far as possible. It's definitely one challenge to really choose the relevant ones. So I would like to offer a second chance for those of you who really struggle but really didn't make any progress from the earlier exercise, right? Let me now switch to my notes before I start doing the exercise together with you, which I think will be necessary for your learning. And so here, just to give you a little more hints, which may not be the case, for test or exam, but at least we want you to make some progress. So these are the relevance inference rules that you may want to consider using in order to really try to, or at least to attempt to prove this sequence over here, right? So that'll be a very big hint to you. And for those of you who really didn't complete the exercise from earlier, from the last video, I would suggest pause the video right now and try to do it by yourself. Otherwise, you will have to do it the first time in the test or in the exam. All right, you can now pause the video. Alright, assuming that you actually pause the video and really try hard to really complete this exercise, let's now do it together to see what's really lacking in your understanding, if there's any. And I'll try to really give you as many insight as possible as I go. But if there's anything that's missing or anything that's not clear, put it on the ask me on the Q&A, or just reach out to me, right? That'll be the best way to really learn about this kind of a formal process. Right, so this is what we want to prove over here, and let me remind you very quickly that, so this part of the goal is the guard for ML out, right? So this is the guard of ML out events. And this part here, the second disjunct, is actually the guard of ML in. And according to the deadlock freedom proof obligation rule, we will have to put things into disjunction, right? That's what we have to do. And we got the hypothesis, and also we got the goal over here, right? So how do we prove it? And let's now look a little bit more closely into what we really want to prove. That will actually suggest what you may actually want to try and try to apply the inference rule. Of course, since I know the solution already, so I'm kind of guiding you towards the right path. But don't be too afraid if you really try something, apply certain inference rule, and somehow you fail. But that's okay. So if you fail, you actually know where things actually didn't work, so that you can backtrack and maybe try to do things in a slightly different way. That's what you really have to do. But for now, to save time, I'll just guide you through the actual correct solution path. Okay, let's take a look at the goal over here. Since one thing that we really want to prove is about n is actually less than d. So for n larger than 0, this one here is simply just about the number of cars in the compound must be strictly larger than 0. That means you need to have at least one car that's actually in the breach island compound. And this one may not be so promising to be proved, because we know that it's actually possible that n is equal to 0, because we may just when the system is first launched, we simply don't have any car in the compound. Well, it's just possible that maybe all the cars in the island, they have already moved back to the island overnight, so there's simply no car over there, right? So this may not be the one we want to prove. What we want to prove instead is actually this particular disjunct over here, n less than d. This might be the one we want to, right? So let me just highlight it. So this might be the one we want to focus on to prove eventually. But how do we do that? So what we can do is we want to find out the relevant hypothesis that can help us on this. And one thing you can try to think, when we say n should be strictly less than d, we are really talking about the upper bound of d. Upper bound of n, the variable n. And so in the hypothesis, we want to find out anything that might help us to really argue about the upper bound for this particular variable n. So what are they? So here, definitely we don't really need this, right? We definitely don't, this is about the constant d's type. And this one here is about n should be larger than or equal to 0. Basically, this is what it is trying to say, because, excuse me, it's actually a natural number. So that may not be very useful either, because here we're talking about the upper bound should be less than d, but here we're just talking about larger than or equal to 0, right? It wouldn't really help if you think about it. So larger than or equal to 0 is not really going to be so helpful in proving that the same variable is less than d. So what seems to be useful is this one over here, n less than or equal to d, right? So this will be the one we want to keep, right? For sure. So this will be something we would like to keep. So in order to prove this one eventually, you can see this one looks very similar, but of course it's not exactly the same, because this one got strictly less than, but this one got less than or equal to. So that's something we want to consider maybe later by other inference rule. Right? It's a very quick justification on why I'm actually choosing the relevant hypothesis like the way I'm going to do. Right? So what I would do, what I would start from would be, first of all, I want to split this particular n less than or equal to d over here to be equivalent to n less than d or n equal to d. Right? That's something we also did earlier. So that I got an n less than d, which will match this particular part of the goal. And we can actually do some other rule application as well. Right? So let me do this. So what I would suggest, whenever you want to do any rewriting, right? For the proof, we definitely want to show every possible step whenever possible. So this will be equivalent to, right? So I'm going to basically copy everything except for this one over here, which I'm going to rewrite. So I have the same thing over here. So let's say here. So we got d is a member of natural number, n is also a natural number. We haven't applied the monotonicity rule to really drop the hypothesis just yet, but we'll do that in the next step. And the only thing that's changed is we're going to rewrite it as n less than d or n equals d, right? Everything else stayed the same. And we got n less than d, which we want to focus on proving ultimately, or n larger than 0, right? So this is what we have over here, right? Hopefully you're okay so far, right? You can see that's exactly what's being changed over here by doing some rewriting, right? And now we can apply the monotonicity rule. And what I will do is I'm going to drop everything except for this one over here, as I just justified earlier, right? So what I will do is I'm going to drop everything except for this one over here. So I'm still keeping that over here. Let's say n less than d or n equals d. And then we're going to get turnstile n less than d or n larger than 0. That's what we have. After dropping the irrelevance hypothesis, right? That's what we got. And what else? Okay, let me just make a little bit more space for later, because we're going to branch out very soon. So you will really see the tree structure for our sequence proof, right? I think that'll be good. Okay. So far we applied, you can think about two rules. One is about rewriting this particular less than or equal to into this. And the other one is by dropping these two irrelevant hypotheses using monotonicity rule. And that's what we got, right? And let's now think about what to do. You can see here we got the hypothesis being a disjunction. In that case, what should we do? If we actually got hypothesis being disjunction, we definitely have a rule that's available. Which one is it? Well, if you look at that, it's going to be this one, right? You can see the or L. And the L over here simply means the disjunction happens to the left of the turnstile, right? Remember the naming convention we spoke about, right? So what we want to do is think about P or Q being the hypothesis. We can split it into two sequence. One will be P here, and the other will be Q here. And whatever hypothesis that used to be there, we're still going to keep it. But in this case, we only got the disjunction being the hypothesis. So we don't have any other like a hypothesis. So it doesn't really apply. But that's okay. And the same goal that we want to prove over here, right? So I'm going to apply this rule over here so that we can talk about two sequences to be proved. One will be using this hypothesis only, the same goal. And the second one will be using this hypothesis and this same goal over here. And that we'll see. Right, so what I will do is I'm going to split it by using the rule for the OR. So I'm going to use the OR left over here, and then I'm going to actually put it in this way. Right, so I'm going to have two sequence. Right, the first one is actually going to let's interpret this rule once more, just for this one here. You can think about what's really happening is this pattern over here is really matching the sequence that we want to transform. You can think about this part over here is the goal over here, and this part over here is the hypothesis that we have, which is a disjunction, right? They are matching. And if they are matching, we can now split them into two sequence over here, which is exactly what I'm going to put over here. And the two sequence is going to have the hypothesis P, hypothesis Q separately, which will be this hypothesis and this hypothesis separately. That's what we will do. Right? Let's now do one by one. And the first one is going to be n less than d. And the second one is going to be n equals d. Right? Everything else stay the same. So the first one is going to n turnstile n less than d or n larger than 0. Right? The same goal. Right? That's the first one. And also the second one, turnstile, and we're going to get n less than d or n larger than 0. Right? That's what we have. So these are the two sequence that we got by applying the OR rule over here. Right? So after this, what should we do? Well, what we should do is we should really take a look at one by one. So think about the rule over here. It's really important to see. Originally, we only got one sequence to prove, but according to this particular inference rule, if you want to prove about this single sequence as the consequent, it will be sufficient to prove the two sequence over here in the antecedents, which will be prove this one here independence of proving this one separately, right? So let's now talk about each one of them. And for this one, I can tell you that it's basically almost done for this one here, because you can see the hypothesis is matching the goal, right? However, let's take a look. It's not exactly matching, right? So we cannot really apply this particular rule just yet. If you think about the hypothesis, right? You can think about P is really matching P over here, but only part of it. So we got some extra bits, which is not allowed by the hypothesis rule. So it would be wrong if you simply just say hypothesis here right away. We can only do that if we can somehow drop this. But we did learn about how to drop this, right? So that means we only want to select the disjunct, left disjunct for the goal. And we did actually learn about it, which will be this one over here. Remember, if the goal is actually a disjunction, it would be sufficient to prove just the left disjunct over here, right? So that's really important to see the thinking process. So we can only try to keep the left disjunct over here. After that, we will be matching exactly the hypothesis. That's what we'll have, right? Let's now do it. So let me first of all drop this one here. That's my intention. By applying the monotonicity rule, so what I will have is I'm going to have n less than d, and then turnstile n less than d, right? Okay, so hopefully, so far you can definitely see the shape of the tree. Think about this is the root of the tree. And then we are getting towards the leaf, the bottom level of the tree, right? Think about in that way. Right, so after this, what's going to happen? So you can see now we are matching exactly the hypothesis rule, right? You can think about H over here is simply absent, which is okay. We just don't have any extra hypothesis. But you can see the P hypothesis matching exactly the goal. N less than D matching exactly N less than D over here, right? So it's proved. And we're going to justify it. So we're going to say by hypothesis axiom rule, so now we are proved, right, for this. So this branch is done, right? So this is independence of this. So now we want to say, we want to see whether or not this part can be discharged as well, right? And for this part, let me make it a little bit smaller so I can write it in a single line. Okay, how about that? Okay, so here, so what should we do? So here you can see some very special shape of the hypothesis for the sequence over here, which is n is equal to d. And this actually corresponds to one of the new rules that we just covered one video ago, right? If we remember over here, right? you can see we got, if part of if you want to prove a sequence where we got as part of the hypothesis E is equal to F, similar to N is equal to D, right? You can think about N over here is the E, and D over here is the F, and it appears as the hypothesis over here. But now the issue is, should we go from left to right, meaning that we're gonna replace E by F, or should we go from right to left, meaning that we're gonna replace F by E? Which way should we choose? It turns out we should really choose the first one. So I'll try to talk about what if you actually chose the other path, which is absolutely possible. In which case, you might just find yourself getting to the dead end. In which case, you may just want to backtrack and choose the other one, right? It's very common, actually, bottleneck that you might just run into when you do the proof. So I just want to show to you, don't really expect things to be so perfect. You can simply start from the beginning, applying all the rules all the way to the end, and then discharge everything. It's not possible, right? But I'm just trying to show you the process, right? So let me, so I deliberately didn't really put an equality rule over there because I really want you to think about which one you want to use, from left to right or right to left, right? It turns out we should really use the one from left to right. So what I will do is I'm going to just paste the rule over here, right? You can definitely take a look, right? So what we want to do is we want to go from left to right. Think about this is E, and this one over here is F, right? You can see at the moment, we actually got dependency on the E and dependency over here on the E over here, right? So if we go from left to right, that means we're actually going to replace every occurrence of N over here by just D. That's what we want to do. Let's do that first. Okay, so we're going to apply the equality rule, and specifically from left to right. So the equality rule from left to right. And we're still going to keep that particular hypothesis, which will be N is equal to D. However, every occurrence of N is going to be replaced by D. So that will be D over here is less than D. Or D over here larger than 0. Right? I try to be very careful about using the pink over here. You can see N over here replaced by D, which correspond to the right hand side. So we are really going from left to right. Right? Exactly. Right? So let's now try to see if there's anything further that we can do. Right? Over here. Right? And of course, don't forget the turnstile. I forgot to put it. Right? So that's what we got. Right? So we got N equals D, and then we got this. Right? It looks like all we got over here is simply inequalities. In that case, having some equality over here is not going to help anyway, right? So we can safely drop this particular hypothesis by applying the monotonicity rule, right? Let's now do that, and then I'll talk about what if you took a different way to for substituting the equality. I'll talk about it. But let's say monotonicity, and then over here, so what's going to happen is we're going to have just the turnstile over here, and then we got D less than or equal to D, or D larger than 0, right? I got just enough space over here. But we're getting there, all right? So that's this one here, right? We simply don't have any hypothesis, which is okay, right? Right, so here, what should we do? Well, basically, we can you can see it's a disjunction of the goal, right? So we can either choose ORL to prove this. D is less than D. D is less than D is definitely false, right? As we know pretty well from the basic mathematical property. A number cannot be less than itself. So our only hope is really to prove this by applying ORR1, sorry, ORR2 over here, right? If we try the ORR1, we're going to prove this, which is false anyway. But if we try to keep this one over here by using ORR2, in that case, we can try to prove D larger than 0. However, for D larger than 0, let me highlight it over here. D larger than 0 is not really provable because based on our original hypothesis over here, there is nothing over there that's going to tell you about a lower bound for the D. All we know about is D is simply just a natural number. So this might suggest there is some flaw or maybe insufficiency of our model, right? That's something you definitely want to C. But I'll talk about exactly how to interpret this proof getting stuck or proof failure in the next part of the lecture. Right? Let me just highlight it over here. And this is what we our only option over here that's left, right? Because we know the other one, like a D less than D, is simply just false, right? This is our only hope. So what I want to do is I want to just draw some connection over here to say this is the only one that could be useful to us. That's the only one. I want to leave a little bit more space because I want to talk about the alternative approach as well. Okay, so that means our model may not be sufficient. M0 may not be sufficient to actually prove this particular one, right? So the conclusion is we actually get stuck over here, right? So after this, I'm going to put a question mark, right? The question mark should really go to the right of this particular sequence, but I don't have space, right? So there should be that's where we got stuck, right? Let me just highlight it once more. But I do want to talk about what if we actually chose a different direction about the equality inference rule, right? Let me talk about it quickly. So this is where we get stuck. Alternatively, let me now write it down. Maybe purple, right? Alternatively, okay. Alternatively, let's say we're still talking about this particular sequence, but let's say we try equality, but from right to left, right? If you go from right to left, I'm not really pasting over here, but basically what's going to happen is we're going to replace every occurrence of D by N. That's what we'll do, right? How do we do that? So what we'll do is we still got N is equal to D, but every occurrence of D by N. So N doesn't change, but D is going to be replaced by N. So we got turnstile N less than N, or that's it, right? And also N larger than 0. Also N larger than 0, right? But now let's see what exactly is happening over here, right? So that's really something you want to also understand about exactly how this is going to work alternatively. So we basically already replaced the D over here by N, right? This is the only thing that we had to replace over here. And if you look at this, of course, we can also apply the monotonicity, right? The monotonicity rule, right? I'm really running out of space, but turnstile N less than N or N larger than 0, right? That's the alternative sequence that we may want to discharge. Is this any way better than this one over here? It turns out it is not, because I'm gonna give you some intuition, and we're gonna discuss in detail. Okay, over here, if you take a look over here, N less than N is similar to D less than D, which is false, right? So these two are equally useless, so the same. But if you think about D larger than 0 versus N larger than 0, right? It turns out this will be more reasonable to really fix our model, to really set maybe some lower limits for the D, to say that the maximum number of cards should be at least 1. So that means you should not really allow the maximum number of cards to just be 0, right? Let me say it again. Remember, D over here, the constant denotes the maximum number of cards that can be in the island bridge compound. And here, if we want to fix this one here, we want to say that particular maximum should be at least 1, larger than 0. And if you want to fix this one accordingly, we want to say that the number of cards that's actually in the island should always be positive, which may not make sense because sometimes maybe overnight, there's simply no car in the bridge and also in the island, right? So that's something I want to write down. It's a very, very quick observation. That's really something you want to see why going from one way, it will be actually better than the other, right? Okay, I want you to compare these two, right? So let's now talk about these two, right? So you can think about this one over here and also this one over here, right? So we got D larger than 0 versus N larger than 0. So what do they mean individually? D larger than 0 simply means the maximum number of cards in the compound is actually larger than or equal to 1. The maximum itself, right? So that means you may have, so that means the maximum number of cards you have is simply 1, right? You cannot really have the maximum number of cards being 0. What does it really mean when you have the maximum number of cards being 0, which is currently the case? It's actually possible because D is actually a natural number. When D is equal to 0, that would mean you can never ever have any card actually in the island compound, bridge compound. In which case your system will never react, right? So that's why this might be easier to fix for us. On the other hand, over here, n larger than 0 over here is really about the number of cards always should be larger than or equal to 1, right? So these two really mean something different. They look similar but very different. If you look at this one over here, right, maximum, and this one, the actual number of cards larger than 1, or larger than or equal to 1. And this one wouldn't really be reasonable to put into your model because, as I said, there might be some time where there's simply just no car on the bridge or the island, right? This one over here, it turns out not reasonable to impose on the model. Whereas this one over here would be reasonable. This one over here, okay? Maximum equals to 0 should be avoided. Right? Really study this intuitive insights about considering either for this path or for this path, right? It turns out this path over here is really the way to go as far as possible. All right? Okay, that's about enough discussion. I think there are many things which I discussed over here that will be valuable to you. So study them carefully, especially about my concluding remarks about whether we should go for this branch or this branch, and also about the discussion over here. It's really important. All right. All right, so that's about the proof which failed, actually, because we actually couldn't really successfully discharge this particular branch. So that means we got to go back to our model and have some reflection and maybe to elaborate our model. We'll see in the next part, right? And if you see the slides, and that's exactly the proof that we have done, except that here I try to combine these two steps together to say, do this followed by monotonicity. But in the iPad notes, I actually try to show to you separate steps over here. That's the only difference. Okay. All right. So now let's talk about how we can revise our model accordingly.